Hi there. This video is the first part of section four, or I guess chapter four, sections 4.1 through 4.3. And the main learning objectives are to explain the difference between empirical probability and theoretical probability. We're going to be calculating the probability of an event, both empirical and theoretical. I'd like you to be able to explain the difference between odds and probabilities and convert between the two of them. We're going to calculate the probability of two events both happening. And there's two versions of two events both happening, dependent and independent. I'll explain those, of course, as we get to that part in the video. Another main learning objective is to calculate the probability of either or two events happening. So there's two events, and again, there's two different ways that two events either or can happen. They're called mutually exclusive and not mutually exclusive or mutually inclusive. We're going to describe and calculate conditional probability, and finally use a table that shows the relationship between two categorical variables, also known as a contingency table, to find the probability of events. Okay, so let's get started with the first learning objective, which is to explain the difference between empirical probability and theoretical probability. So what I've done here is I started off with just some letters, some notation that we use pretty much all the time, just to clarify these letters, these notations that we use. And then I kind of have a table here, a side-by-side comparison, so you can know the difference between empirical and theoretical probability. So with the letters we typically use a capital letter like an A or a B to represent some event happening. It rains or you win the lottery or something, right? So a capital letter, is an event happening, and P parentheses A is the probability of that event happening. When PA is zero, which is the same as 0%, we say that A will never happen. That event will never ever occur. It's impossible to occur. And when we say the probability of event A happening is one, which is one as a number is the same as 100%, that means A will always happen. No matter what, it's assured that A will happen. So we have like never to always, 0 to 1. So our probabilities will most likely be between 0 and 1. Certainly can't be less often than never, and can't be more often than always. So probabilities are between 0 and 1, between 0% and 100%. Okay, so what is the difference between empirical probability and theoretical probability? So for empirical probability, it's based on a study. And there's two types of studies from our previous sections of the book, observation and experiment. Experiment is when you give a treatment to some of the subjects. Observations, you just view, you're not going to give any treatments. But whichever kind of study you use, you're going to observe stuff and you can calculate empirical probability. Whereas a theoretical probability is a result of a calculation. You're going to use some formulas. So this is kind of the big difference. The empirical is a result of a study, and the theoretical is a result of a calculation. So let me go down and explain empirical first, and then I'll do a theoretical second. So for an empirical probability, we got to have our observation. We have to know the size of the study, the number of people that could possibly be observed, and or the number of observations that we actually did, and the number of times that the event occurred. And our formula is this one right here. We just count how many times the event occurred, the total number of observations. You make a fraction. The number of times it occurred out of the total number of observations is called the empirical probability, and they write it as PA, probability of event happening. So I have an example just to make things a little bit more concrete. So suppose my event A is a 3 shows up on top of a die. Math people love like games of chance and stuff, so they see a lot of dice and cards and things like that in the homework examples. I have some of those, and I have some other ones, just so you can see a variety of probabilities. So this one is a die roll, and a 3 shows up on top of the die. So we did a study, and the study says a die is rolled 50 times, and it was reported or recorded that 3 showed up 9 times. So what's our probability? Well, it's the number of times that the event happened divided by the total number of observations. We know that we got a 3 9 times, and we know that there are 50 rolls of the dice. So there's 9 threes that occurred out of a total of 50 rolls or 50 observations. So 9 out of 50 is our probability, and you can convert that into a decimal, which is 0.18, or you can convert that to a percent, 18%. So that's our empirical probability that this study, what this study showed was the empirical probability of 18%. All right, so now let's look at the theoretical probability. Oh, I didn't color code this like I hoped. Okay, well, time to change on the color. So empirical probability was an observation. Theoretical probability is a prediction. So we're not actually collecting information. We're just making a prediction about what we think is going to happen. And the way we make this prediction is we use a formula. It's a similar formula, but we do have to know certain things. We must know all the possible outcomes, and we also have to know that they're equally likely to occur. And the formula for the theoretical probability is the number of ways that the event A could happen out of or divided by the total number of possible outcomes. Again, I'll give you an example to make things a little more concrete. So here's the example with the 3 again. So the event is a 3 shows on top of the die, but we also need to have knowledge. Remember, we must know all the possible outcomes and that they're equally likely. So our knowledge for the theoretical probability is it's a 6-sided die. All 6 dies are equally likely to occur, and there's only one 3. Only one side has the number 3. So that's the knowledge we need. Now, you may reflect on the fact that we don't actually need to know any of that for empirical probability. It's literally how many times 3 showed up. It didn't have to be a 6-sided die. It could have had other sides or more than one 3. It didn't matter because empirical probability is just the results of a study. We rolled the die 50 times, 9 of them came up 3s, 3 out of 50, that's our probability. With theoretical probability, we have to know a lot more. So I have to know how many sides are in the die. We have to know how many 3s are. We have to know that it's like a real die that's not like weirdly weighted or something so that others come up more often. So there's a lot more knowledge that has to happen for theoretical probability. And then we have our number of ways can happen. Well, only one of the sides has a 3 on it. So there's a 1 up there. And the total possible outcomes, well, there's 6 sides. So it's 1 out of 6. One possible side with a 3 out of 6 possible sides or 6 possible outcomes. So our theoretical probability is 1 out of 6. And if you convert that to a percentage, it's about 16.7%. So both events were the same. One was an empirical probability calculation because we did a study. The other was a theoretical probability because we kind of sort of thought about what was possible and we figured out the formula based on that. Just a little note here, due to the variability of life, in other words, like there's random chance of stuff, even under ideal conditions, the empirical probability will not be exactly the same as the theoretical probability. So even though we both are doing like the 3 shows up on a die, they won't necessarily be the same. If you do an empirical probability for lots and lots and lots and lots and lots and lots and lots of observations, like tons and tons of time, not 50 times, not like 5,000 or 500,000, like you have to do it for a lot of times, then the empirical probability will get closer and closer and closer to the theoretical probability. But that's for another chapter. And let's see, let me do this. Yeah, turn off my phone ringer. Anyway, so that's something that you'll study in a later chapter, that these two probabilities will get closer together, but that's only if you do a study a whole bunch of times. All right, let's go on to our next learning objective. We're going to be able to calculate the probability event, both empirical and theoretical. So we just did the event, a 3 shows up, and we got for the empirical probability for a 3 showing up, we got 9 out of 50 or 18%. And for the theoretical probability, we got 1 out of 6 or 16.7%. So those are the probabilities for the event happening. We can also talk about the probability that A not happen. So not A does not happen. So we can talk about it with both empirical probability and theoretical. So for empirical, I can't spell. Empirical, I can't write either. Empirical probability and theoretical probability. All right, that one comes out a little nicer. So for empirical, again, pretend that says empirical, right? We know that for A happening, empirical probability was, well, let's just double check. For empirical probability, the event was 9 out of 50 or 18%. So if it doesn't happen, well, it's got to be the other 41 out of 50 or the other part of 100%. So 18% was it happening. So what's not happening, so 18% A happened. So we can just do 100% minus 18%. And that will give us, well, I think that's 82%. So that's the probability that not A happens. A happens 18% of the time. So not A has to be the leftover 82% of the time. And for theoretical, it was 1 out of 6 or 16.7%. I'll just verify that with you. 16.7% was the amount for the theoretical probability of a 3 coming up. So what's the probability that not A happens? Well, we know that 16.7% A happened for the theoretical version. So our not A would be 100% minus 18%. No, 100% minus 16.7%, which is approximately 83.3%. Okay, so there's the example of how to find not A happening. Let's do something a little bit more interesting than just rolling a 3 on a die and getting a 3 or not a 3 or something like that. Here's another example that's not so like, based in games of chance. My example B right here is an automatic cat food dispenser is set to give between 18 and 20 pieces of of cat food or cat kibble every 6 hours. So this automatic dispenser, every 6 hours, it shoots out a bunch of cat kibble, and the cat or cats can have some food at that time. So what's my event? My event is the food dispenser gives at least 18 pieces of cat kibble. And then we want to find the probability that this occurs, and we can also find the probability that it doesn't occur. So a lot of times students make a mistake here because they're just going too fast. And they're like, okay, 16 to 20 is 4, 18. So, they start doing those things. But what I recommend is you just spend a little, I know it's kind of like, not the most efficient in terms of time, but spend a little bit of time just writing out between 16 and 20. Well, that means 16 pieces of cat kibble are possible, or 17, or 18, or 19, or 20. Those are between 16 and 20 pieces of cat food. Notice that there are 5 different numbers there that could happen, right? So for our theoretical probability, we have to know stuff. We know that there's between 16 and 20, which are 5 different things. And if you just subtract 20 minus 16, you get 4. And that's the mistake I see a bunch of students make because they're just doing it kind of quick. And they don't realize it's actually 5 different options there are between 16 and 20. All right. So how many of these are at least 18? Well, at least means 18 or more. So here's at least 18. So that's 3 things that match our event, 3 things that our event A, the dispenser gave at least 18 pieces of candy. Or why did I say candy? I guess my cats think of cat kibble as candy, maybe. So 3 out of those 5 is at least 18 pieces of cat food. And so our probability would be 3 out of 5. That's the number of ways that the event could happen. There's 3 ways that the event could happen out of a total of 5 possible things that could happen. So 3 out of 5. What about the probability of not A? Well, if 3 out of 5 is the probability that A occurs, then not A would have to be the other 2 out of 5. There are 2 out of 5 which are not at least 18. And you can kind of see them right over here. These two right here are the 2 out of 5 that aren't at least 18 or not event A. 3 out of 5, if you want to convert it to a decimal, is 0.6, or as a percentage, it's 60%. 2 out of 5 is 0.4 or 40%. And you can also see like 100% minus 60% is the 40%. Like, the not is always 100% minus the is, right? So the two together have to make the 100%. It happens, it doesn't happen, it's got to be one of those two. All right, so that's an example of some probabilities of events occurring and how you think about those. All right, next up is to try to explain the difference between odds and probability. This can be a kind of a matter of confusion if you're not careful about what odds are measuring and what probability are measuring. Some people got to get them mixed up a little bit. All right, so I have here a little box to maybe give you a thing to focus on. Odds will always compare the number of times that an event occurs to the number of times it does not occur. So it basically does the number of times A occurs to the number of times not A occurs, right? So it's A to not A. Whereas probability, as we've done several times before, is the number of times A occurs divided by the total number of possible outcomes. So you're kind of measuring two different things. Odds is it occurs to it doesn't occur. Probability is it occurs out of the number of possible outcomes. All right, so again, let's do some examples to make it a little bit more easy to see what's going on here. All right, so we're going back to our 3 shows up on top of a die. So remember, we talked about, for at least our theoretical probability, that with a 6-sided die and only one 3, and all the sides are equally likely, that the probability of the event happening is 1 out of 6. That was our 16.7%. And our not A is 5 out of 6. So 5 out of 6 would be our 83.3%. So those are just things we did previously in this lecture video here. So the odds are the number of times A could occur, which is 1, and then 2, the word 2, and then the number of ways A does not occur, 5. So we would say the odds are 1 to 5 that event A happens, or the odds are 1 to 5 that a 3 shows up on top of the die. Whereas the probability is 1 out of 6. There's 1 3 out of 6 possible sides. So 1 out of 6, as we know, is the probability that occurs, but the odds are not the same thing. They're measuring the number of ways that the event could occur to the number of ways the event does not occur. Sometimes they write events as like 1:5. That's just an abbreviation for 1 to 5. Even if you see 1:5, you're supposed to read it as 1 to 5. Just the colon is the abbreviation sometimes used. And 1 out of 6, as you've seen before, is oftentimes abbreviated as a fraction. So this would be 1 out of 6 or 1/6 of the time. All right, so that's the difference between odds and probability. Let's do another example of that. Let's do our cat food dispenser, or cat candy dispenser, as I keep saying. So we got our cat food dispenser. It's doing 16 to 20 pieces of kibble every 6 hours, just like before. And just like before, the event is at least 18 pieces of cat kibble. So nothing's changed in terms of the type of example. I'm just now trying to focus on the difference between odds and probabilities. So as we discussed before, as we calculated before, to get 18 is 3 out of 5. There were 18. There were 5 possible amounts of kibble: 16, 17, 18, 19, 20. 3 of them were the ones that were 18, at least 18. So that was 3 out of 5, or 60%. So just going back down here, reiterating this example, it's the same example before. Our probability that A occurs is 3 out of 5. There's 18, 19, 20 out of the 5 possibilities. So that's the theoretical probability, 3 out of 5. So the ways that A does not occur, as we found out before, is 2 out of 5. So what are the odds of event happening? Okay, if you thought about what that's going to be before I write it, it's going to be 3, 2, 2. It's the number of ways A can occur, which is 3, 2, the number of ways A does not occur, so 3 to 2. And the probability, well, that is 3 out of 5, or 3 out of 5, like that. So there's another example of the difference between odds and probability. And then you can see that these two added together, the 3 and the 2, that's the ways A can occur, and the ways A can occur, that's the total number of ways. So that's the number that goes down here. That's the 5. So that's how you can translate between odds and probability. All right, so for the next learning objective, I'm actually going to kind of do 3 altogether. It's kind of easier to talk about 3 of these together than try to isolate them separately. So the 3 that I'm going to do over here or next is to calculate the probability of 2 events both happening. That's sort of an and, this and that. The probability that 2 things either or happen, and then describe what conditional probability is and calculate that as well. So we're going to do those 3 all together. All right, for these kinds of things, we need to be considering now 2 events. So the probability of 2 events both happening, there's got to be 2 events. So I'll just call them event A and event B. So those are my 2 events. And so I'll just start off with some examples, and then I'll give you some formulas. So we've already done this example before. I'm going to use the same kind of example just so that you're just really familiar with the way it works and not wrapped up in all the details of each example. So I'm going to go to my die rolling example. So a 3 is a die. Remember, it's a 6-sided die. All the sides are equally likely. There's only one 3, etc. Right. So same example as before. And event B will be the cat food / candy dispenser, where there's 16 to 20 pieces of cat kibble. And the event B is we get at least 18 pieces of the cat food from the dispenser. All right, so we're going to start off by doing an and. We want the probability that both a 3 shows up on top of the die, that's event A, and the food dispenser gives at least 18 pieces of cat kibble, that's event B. So I can arrange these visually into a little chart. So for the die roll, there are 6 possible die rolls: 1, 2, 3, 4, 5, 6, and a 3 is all of these guys. These are all the 3s, right? So a 3. The reason why I have a chart here is because there are 5 possible kibble amounts dispensed, and there's the 5 of these: 16, 17, 18, 19, 20. The 18s are all here. 19 and 20. I don't know if this is more distracting than not, but there are basically 1 out of 6 of the die roll that we like, and 3 out of 5 of the kibble dispense that we like, that would match the, like is maybe the wrong word, that would match our probability of both happening. So I'm going to show you a couple ways to think about this just to help you understand a little bit more what's going on here. So there are, well, there's 1, 2, 3, 4, 5, 6 different die rolls, and 1, 2, 3, 4, 5 different kibble amounts. So if I just kind of arrange them in this like square, and if you think about how you can add up these squares, there's 1, 2, 3, 4, 5, 6. There's another row of 6. There's 5 rows of 6, or 6 times 5 is there's 30 cells here. There's 30 squares, or cells we call them, right? Because it's 6 times 5. Right, so we know there's 6 possible die rolls, 5 possible kibble amounts, so we get 30 different cells. So how many of those are both A and B? Well, that's what I've shaded in here. This is a 3 and at least 18. Right, otherwise it's just either not 3 or not 18, 19, or 20. Right, all the other ones are at least one of them is not true. So the probability should be 3. There are 3 things that match A and B out of a total of 30 different things that could happen, right? There's 30 different cells. and 3 of them match the criteria that both of them happen. 3 out of 30, we could simplify that to be 1 out of 10 just by proportionally dividing the top and bottom by 3. All right, so that is the probability that both A and B occur. We can literally just count it. We have a special formula. Oh, by the way, I want you to note that A and B are called independent events because one event will not affect the other event, right? The die roll will have no effect on the food dispenser amount, and the food dispenser will have no effect on the die roll result, right? These are completely independent events, which means one does not affect the other one from occurring. If you have 2 events and you want them both to occur and they are independent events, right? So one does not affect the other, then the formula for the probability that A and B occur is the probability that A occurs times the probability B occurs. Let's see what that would mean in this exact problem. So A is, whoops, I'm going to scroll up a little bit. A is the 3 comes up, right? The probability that event A happens just by itself is, well, we've done this a couple times before. There's 1 3 out of 6 possible sides. And the probability that B occurs, well, we've also done this before. There are 3 possible amounts that are 18 or more, 18, 19, and 20, out of 5 possible amounts that could come out. So according to this formula, the probability of A and B occurring is the probability of A times the probability of B. Well, probability A is 1/6. The probability of B is 3/5. And let's multiply those two fractions together. To multiply fractions, I just multiply across the top. 1 times 3 is 3. And multiply across the bottom, 6 times 5 is 30. And you can see I get the same result as I got before. By just counting the number of cells, there are 3 of them that match our A and B happens out of 30 possible. But you could just multiply the two things together, 1 out of 6 times 3 out of 5, and get the exact same result, 3 out of 30. This is important because if we get many more kind of results, our grid gets much bigger. It becomes less practical to count and becomes much easier just to multiply numbers together. So we definitely want to know this rule when things get a little unwieldy for us to draw and count. All right, those were for 2 independent events, right? Things that one cannot affect the other. All right, so let's talk about this second example B. A standard deck of playing cards has 52 cards, 4 of which are aces. So there's 4 aces out of 52 cards. My event A is an ace is randomly chosen from a deck of cards. So you randomly choose a card and it comes up an ace. The card is then returned to the deck. Event B is an ace is randomly chosen from the deck. And so it's the same, right? So event B is the same thing. The ace is randomly chosen from a deck of cards, and then the card is returned to the deck. So are these events independent or dependent? Well, event A, I'm going to choose a card, and it's an ace, and I'm going to return it to the deck. Does this deck still have 52 cards? It does, because I returned that card back. Does it still have 4 aces? Yes, it does, because I returned that ace back to the deck. So if event A occurs, I still have 4 aces out of 52 cards for event B. If event A doesn't occur, remember I'm still returning the card to the deck, then again, there's still 4 aces and there's still 52 cards. So these are independent events because whether I draw an ace on the first draw doesn't affect whether I draw an ace on the second draw. And whether I draw an ace in the second draw is not affected by, does not affect my first draw. So they're independent events. So we know the probability of A and B occurring is just the multiplication of the probability of A and the probability of B. But what is the probability of A? Well, we know that there are 4 things that match this description of event A, right? There are 4 aces, and we know there are 52 possible outcomes. And let's just assume that that all 52 cards are equally likely to be picked. There's no like weird bent corner card that comes up more or anything like that. So the probability of event A, let me make a little bit more space here, is 4 out of 52. Probability of B, well, remember we return the card, so there's still 4 aces. There's still 52 cards in the deck, so it's also 4 out of 52. So we multiply those two together, and that with the probability of A and B, because A and B are independent events. We should simplify this to make things easier. It's 1 out of 13 times 1 out of 13, which I believe is 1 out of 169, if I remember 13 times 13. You could check on a calculator. That's the probability of getting an ace, putting the card back, and then drawing another ace. Not very likely, but definitely possible. 1 out of 169 times, you will get an ace, and put it back, and then draw another ace randomly. All right, well, we got 2 versions of independent. Maybe we should look at something in which they're dependent. All right, so I have a new example here, new type of example. We have a Halloween candy bag. So we got a bag of candy. I guess I should make it red because I think red's a Halloween color. I don't know. There's a bag of candy. Inside the candy is you got some green, you got some blue. Whoops, that was not green at all. You got some green candies. You got some blue candies. And you got some, I don't have a yellow on this. I'll just call it black yellow. We got 3 of those. So we got 3 that are a very dark yellow. So those are my 10 candies in the bag. And without looking, I reach in there and I grab a candy randomly taken from the bag. And event A is it's going to be blue and you eat it. Event B, you reach into the bag. A second candy is randomly taken from the bag. It's also blue and you also eat it. Okay, so those are the 2 events, A and B. So we're going to try to find the probability that A and B occur. Now, I want to distinguish between this event and the previous event. These are A and B are dependent events. They're dependent events. Why are they dependent? Because if I get a blue candy my first time, if event A happens and I get a blue candy and I eat it, there are now only 9 candies left in the bag. And in fact, of those 9 candies, only 5 of them are blue because I ate one of them, right? So the fact that A happens will have an effect on whether B could happen, which means that whether or not I draw a blue candy out of the bag and eat it will definitely change or influence or affect the probability of my second candy also being blue, right? Because there's a different number of candies, and presumably there might be a different number of blues if I got a blue and ate it. So these are dependent events. So what's going to happen here? Well, if I think about this, there are 6 blue candies out of 10. So for my first thing, probability of event A happening, there are 6 blue candies out of 10 possible candies to be drawn. So 6 out of 10 is my first probability, my first event happening, which is getting a blue and eating it. What about the next one? Next number, look, the next number I have here is 5 out of 9. Where does that come from? Well, if I've successfully taken and eaten a blue candy, how many candies are left? So after this, well, I've eaten a candy, so there are 9 candies left, right? Because there's one that's eaten now. There was 10, now there's 9. And how many are blue? Well, there were 6 blue, and so now there are 5 blue left. So now I have a new bag. I mean, I guess it's the same bag, but a sort of a new version of the bag where there are only 9 candies in my Halloween bag, and 5 of them are blue. That's where the 5 out of 9 comes from. For my second candy, my second random piece of candy, there are 9 possible candies to choose from, and 5 of them are blue. So I have to take into account that A has already occurred when I'm trying to calculate my probability of B, And now I can multiply them together as before, but notice I just can't multiply them straight. I have to assume that one has occurred because it changes the probability that the next one will occur. So I can multiply across the top. 6 times 5 is 30. Multiply across the bottom. 10 times 9 is 90. I can simplify this I can divide by 10, and I can divide by 3. So it's 1 out of 3. 1 out of 3 chance that I both A, draw a blue candy and eat it, and B, I draw a second blue candy and eat it. Okay, so 1 out of 3 chance that I get 2 blue candies in a row. And now we have, of course, a formula, the probability for dependent events, right? So if you're having A and B, you want both of these things to happen. The probability of A and B is this kind of weird formula. A lot of people look at this and they go, what? Okay, so let's just break it down. Probability of A, that's just the first thing, right? 6 out of 10, that was just you got a bag, 10 candies, 6 are blue, 6 out of 10, boom. So that's the same thing. The second one is the one that messes people up a bit. So what is this PB/A? The way math people read this is the probability that B happens given that A has already taken into effect. Because remember, the fact that A happens affects what happens with B. So PBA, probability that B happens given that A has already occurred, is what that funny thing is. So when you see that vertical line, it's red given. So probability over here, probability that B occurs given that A has already occurred. So that's what PB/A is. And it's funny as that looks or sounds, that's exactly what we did. To get the 5 out of 9, we said, okay, well, we know there's 1 candy less in the bag, and we know there's 1 blue fewer in the bag. So instead of 6 out of 10, it's 5 out of 9. So we did that without using the funny notation or discussion, but math people love their symbols and letters and formulas. So you're going to see P, B, vertical line A quite a bit. That just means let's assume A has already happened, and let's find the probability that B now occurs as well. Okay, so that's an example for dependent events. You just have to take one at a time and find the probability of B given that A has already occurred and multiply those two together. So those are the probabilities of A and B occurring. Let's talk about the probability that A or B happen. So probability of A or B happen. So go back to my Halloween candy bag. So I got 10 candies, 1 green, 3 yellow, 6 blue, same as before. Let's say event A. So again, we pick a candy out. The first candy randomly taken is blue. So the first candy taken is blue. Event B is the first candy taken is yellow. I didn't say second candy. Event B says first candy also. So event A and event B cannot both happen. My first candy could be blue or not. My first candy could be yellow or not, but it cannot be both blue and yellow, right? There's not a half blue, half yellow candy in the bag. It's going to be blue, it's going to be yellow, or it's going to be the other one green, right? So it's either A or B or neither. You can't have A and B. So we call this mutually exclusive. Mutually exclusive means that both things cannot occur. If one event occurs, then it is impossible for the other event to occur. And so we can just add these up. The probability that the first candy is blue is 6 out of 10. The probability the first candy is yellow is 3 out of 10. Remember, there's 3 yellow out of 10, right? We haven't taken anything out, so there's still 10 candies. So we could just say, well, it's either 6 out of 10 or 3 out of 10 for it being blue or being yellow. So we can literally just add those two probabilities up, and we get 9 out of 10, which is 90%. And for those of you who kind of like to think about like how this all makes sense together, there's only one thing that's not blue or yellow, right? It's green, right? There's only one thing that could be not blue or yellow, and that's the green. So the not A or B has to be 1 out of 10, which is then the 10% that makes up the 100% total. So I don't know if that helps you, but you can think of it that way as well. There's only one green, so 10% chance to get a green. Everything else is yellow or blue, so it's 90% yellow or blue. It's the not green is going to be 90%. All right, and the rule here for mutually exclusive events is you just add the probabilities together. So the probability of A or B is probability of A plus probability B, and that's only for mutually exclusive, right? So they cannot both happen. Okay, let's move on to our next page, the second to last page. So we're gonna now look at our example from before. So we have some examples we did before. So I'm doing the die rolling thing. A 3 shows up, 6-sided die, etc. Right? It's the same event before. Like a 3 shows up, and we get the cat food / candy dispenser with at least 18 pieces of candy when the dispenser gives between 16 and 20 food every time. And I'll show you my little chart here. And we're going to talk about the probability of A or B. So we're going to have the probability that a 3 shows up or that the dispenser gives at least 18 pieces of cat kibble. So I've tried to show you here on the chart. This is where a 3 occurs. This is where we have at least 18, 19, and 20, right? So that's this one right here. And so there are 30 possibilities. There's 30 cells, 30 pairs of things that could happen. So how many of those would be A or B? A 3 or an 18, 19, 20? Well, we can just count again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So of these, there's 20, right? 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 out of 30 that match that description, right? It could be a 3 or at least 18. So 20 out of 30, which is 2 out of 3, would be our answer for A or B. And so this is just count them up and you get the answer. But as we said before, like the examples get more complicated. You don't want to rely on drawing a picture every time. It can get kind of messy to count everything out. So we need to sort of have formulas to help us with the counting when things get kind of unruly. So can we just add these things together? Unfortunately, it does not work that way because they are not mutually exclusive. So we call it mutually inclusive, or I think a lot of books call it not mutually exclusive. All right. So that's the same thing, right? Mutually inclusive, not mutually exclusive. I think those are used synonymously. So in this time, what do we mean there? Well, we could have both things happen. We could roll a 3 and we could get 18 pieces of cat food, right? Both events could occur. In our previous example, just to kind of reiterate, on our previous example, we could not have both the first candy being blue and the first candy being yellow. There's only one candy. It can't be both blue and yellow. So that was exclusive when they both cannot happen. But now they both could happen. It's definitely possible for me to get a roll of 3. It's definitely possible for me to also get 18 or more pieces of the cat food. So this is not mutually exclusive or mutually inclusive. So our formula is going to be a little bit different. And what you may see here on the chart is if I just think about the probabilities here, right, which is my sort of 3 out of 5, and I just think of my probabilities here, which is my 1 out of 6, right? So I get 1 out of 6 times I could roll a 3. I get 3 out of 5 that I can do an 18, 19, and 20. Those I can add together, but when I add them together, I'm double counting these 3 cells, right? So I can count this interior stuff right here, but it's both a 3 and an 18, 19, 20. So if I'm counting without thinking of actually counting or just adding them together, I double count these 3 squares. So I have to subtract off those 3 squares I have to minus the 3 out of 20, 3 out of 30, excuse me, in order to correctly count the number of events that match A or B happening. So it's 1 out of 6 for the die roll. It's 3 out of 5 for the kibble dispensed, and then it's 3 out of 30 for them both happening. How do we get 3 out of 30? Well, for both happening, that's two things and happening. Both happening is and. So for and, right, probability that A and B happen, we're going to multiply the probability of event A, which is 1 out of 6, times the probability of B, which is 3 out of 5. Neither one has an effect on the other, so they're independent events. And so 3 out of 30 would be what I subtract off. So there's my 3 out of 30. So if we can't count for practical reasons, or we don't want to, we can add the two probabilities together, 1 out of 6 and 3 out of 5, but we subtract off the probability that they both occur, which is 3 out of 30. To add these up, you might want to get common denominators, which would be 30, and then you can combine them together. 5 out of 30 and 18 out of 30 is 23 out of 30, minus 3 out of 30 is 20 out of 30. And we do get the same result as when we counted things out. Just wanted to show you we get the same result. So you get 2/3 or 20 out of 30, whether you count the cells or whether you do the formula. And of course, I give you the formula in symbols. So the formula in symbols is right down here. If you have mutually inclusive or not mutually exclusive events, right? So either of these, you're not mutually exclusive or mutually inclusive events, then to find the probability that one or the other happens, you basically take the probability of each one added together, but you have to subtract off the probability that they both occur, right? So that's what we did over here. We took the A, oh, my colors got mixed up. We took the A and the B right here, added them together, and then we subtracted off the probability that they both occur at the same time. So that's your not mutually exclusive, your mutually inclusive or formula. All right, so let's do a little example here just to see those in kind of a couple more examples here to get a handle of this. So you get a probability that an ace is drawn from a deck of cards. So we saw that before. That is 4 out of 52. There's 4 aces out of 52 cards. A blue candy is chosen, so that's our 6 out of 10. Right? So we want the probability that one or the other happens. Are these exclusive or not mutually exclusive? Are they exclusive or inclusive? Well, is it possible for both things to happen? Is it possible for you to draw an ace and to get a blue candy you get to eat? Yeah, I mean, you could definitely get an ace. So there are not mutually exclusive, right? So this is the fancy formula one. So I can add together the 4 out of 52 and the 6 out of 10, but then I have to subtract off the probability that they both occur. The probability they both occur would be the 4 out of 52 times 6 out of 10. They're independent events, so we just multiply those two together, and that would be the A and B, this part right here that we're subtracting off. So we got a bunch of little math formulas here to do. And you can work it out. It works out to be 41 out of 65. You can also do it as a decimal, although you got to be careful when rounding decimals. You might want to do the whole calculation at once in your calculator to be able to get the correct decimal at the end, as opposed to rounding step by step. That will give you the wrong answer eventually, as if you round too many times, the answer comes off pretty bad. So we can also just simplify these, like 4 out of 52 is the same as 1 out of 13. 6 out of 10 is the same thing as 3 out of 5. And so you would have the formula 1 out of 13 plus 3 out of 5 minus, I have to multiply the two together, 1 out of 13 times 3 out of 5. And these numbers are much smaller, easier to work with. So 1 out of 13 is the same thing as 5 out of 65. And 3 out of 5 is the same thing as 39 out of 65. It's a plus. And then 1 over 13 times 3 over 5 is 3 out of 65. And then 65. And then you can see 5 plus 39 is 44, minus 3 is 41. So you maybe if you are good at fractions, you can also quickly get 41 out of 65 for the probability that an ace is drawn from the deck or a blue candy is chosen from the bag. Okay, so I think I've done enough for that problem in terms of how that works. So let's talk about the probability that a yellow candy is chosen, vertical line, given that a blue candy is chosen first. So we're going to do this one over here, part G, example G. Probability yellow candy is chosen given that a blue candy is chosen first. So we know that a blue candy has been chosen first. So this is given this has happened. Given this has happened. Well, this is what we did before. Like we know the blue candy is chosen. So for the yellow candy, for this thing right over here, how many candies left? Well, we know that a blue candy was chosen first. So this already has happened. So there's 9 candies left. And how many of them are yellow? Remember, we need yellow candy. Well, the first time a blue candy was chosen, it definitely took 1 blue candy away. So there's only 5 blue candies left in the bag, but there's still the same number of yellow candies as there were before. And if you're not familiar with how many yellow candies, we'll just have to go back to where it's describing how many yellow candies there were. There it is: 1 green, 3 yellow, and 6 blue. So when we take a blue candy out, yeah, there's only 5 blue, but there's still 3 yellow. We never take a yellow out. So there's still 3 yellows left in our bag. Okay, so there are 9 candies left. How many of them are yellow? 3 yellow left. Or maybe still. Right? So we know a blue candy was chosen first. So yank, get the candy out, eat it. So we know that there's 1 fewer candy in the bag. So there's 9 candies left. How many of those are yellow? Well, there's still 3 yellow because we ate a blue one. We didn't eat a yellow one. So what is the probability that a yellow candy is chosen? Well, there are 3 yellows. I ran out of room here, sorry. 3 yellows, so this equal to out of 9 possible candies. So 3 out of 9, which simplifies to be 1 out of 3. I put the answers over here just to help smooth out the thing. And also for people, if they want to pause the video, try a problem, and then they can check to see if they got the right result there. If you don't want to, that's okay, but it's always nice to try things, see how you're getting it. And if you do get stuck, you know where you get stuck, and then you can sort of, continue watching the video to see how to get unstuck. But that knowledge of what you got and what you still need to sort of, learn to do better, that is called learning. That is kind of what we do, right? As humans, we try things and then we fix things that don't quite work well. All right, my third example here, my last example for this page, we have the probability the first candy chosen is blue, and then the second candy chosen is yellow. A lot of times people see G and H as kind of a similar problem. So just reflect on the fact that G says that we're just looking for the probability the yellow candy is chosen, but we know that a blue candy has been chosen first. Whereas in this new question, we have the probability that both the first candy is blue and then the second candy is also chosen is yellow, right? So there's an and here versus a given before. So given means it's already occurred. We know that's a fact. We're just looking for the probability of yellow. Whereas in H here, there's no given. We're just looking for the probability that both things happen. All right. So probability that the first candy chosen is blue. Well, that's 6 out of 10. And then the second candy chosen is yellow. Are these completely independent events? No, because when I choose my first candy and I get a blue, there are fewer candies left in the bag. There's also fewer blues left in the bag. So the first event has an effect on the second event. So these are not independent events, right? So I have to do the probability that now the first candy chosen is blue, and then find out the probability that the second candy is yellow, given that the first candy is blue. But we just did that, right? That was our 3 out of 9 thing, right? That was our, we know that the first candy is blue. So there are 3 yellows still in the bag out of 9 possible candies. So 3 out of 9. So we're using basically our answer in G to help us do H, because they are a different thing. Probability of H means they both occur. So you have to multiply the first event times the probability that the second event occurs, given the first event has already occurred. And this is, well, we can simplify 6 out of 10 is 3 out of 5. 3 out of 9 is 1 out of 3. Now I can multiply across the top. 3 times 1 is 3. Multiply across the bottom. 5 times 3 is 15. And I can simplify to be 1 out of 5, which is in fact the answer that I got previously. All right, so those are some examples of and, or, and given, right? So kind of put all those examples together to kind of see them side by side about calculations. So a lot of stuff you'll be doing in these chapter 3 homework assignments are and, or given probability statements. So two events both occur, one or the other occurs, or one occurs given that the other one has already occurred. Those are the 3 things you got to watch out for. All right, we do have one last learning objective, which is to use a table that shows the relationship between 2 categorical variables. This is also called a contingency table, to find the probability of events. So I have here a table I stole off the internet, where we have one variable is the station number. So we have station 1, station 2, station 3. That's our X variable. X is the station number. And the other variable, I'll just call Y because I'm a boring math person, is the type of service performed at the station. So oil change, tire rotation, or a tune-up, right? So there's different station numbers, and there's different types of service that can be formed at each of those stations. And then the numbers are the number of customers that were served. So 100 customers were served at station 1 to get an oil change, right? So that's the number that sort of represent the station number and the type of service at that station number. So that's what a contingency table looks like. It's got 2 different variables, and we're comparing the 2. If your contingency table does not already have a total, I would highly recommend that you do the totals for all of these. Whoops, come on, where's my pen? There we go. Totals for all these. So how do we get this? Well, and there's totals down here, by the way, too. There's 2 sets of totals. So how do I get these? Well, this would be the total number of oil. See, oil changes is 100, 36, and 92. If I take 136 and 92, I get 328. That's the total number of oil changes, right? 100 at station 1, 36 at station 2, 92 at station 3. So altogether, all the possible oil changes are 100 plus 36 plus 92. And if you add those up, you get 228. And likewise for tire rotations, we add the 50 here and the 35 here and the 102 to get 187. And then the vertical totals are the same way. How many things that did happen at station 1? Well, 100 oil changes, 50 of the tire rotations, and 60 tune-ups. So these 3 things were all the things that happened in station 1. Then 100 oil changes, 50 tire rotations, and 60 tune-ups. So you add those together, 100 plus 50 plus 60. So the totals just add up to be the horizontal rows and the vertical rows. So that's all the totals are. And this would be the total. So the total of all different things, the total of all of the different stations, and the total of all the different types of services. And you can literally just add these things together, either horizontally or vertically. You can add 210 plus 111 plus 279. So you can add these numbers, 210 plus 111 plus 279, and that will equal 600. Or you can add the verticals. You can add 228 and 187 and 185, and you also get 600. So it just basically says like that's the total number of things that happened, and you can get that by adding all the different types of services, or you can add that by doing all the different types of stations. All right, so that's what a contingency table looks like, and if it doesn't have a total on your table, definitely I would think the problem becomes way easier if you just put the totals, make a new like end column or row and just say the total for each row and total for each column. Okay. And you also know, by the way, that there are 600 different things that happen, 600 customers, we call it. 600 things happen at all these different stations and types of services. So that 600 told us the total amount of things that could happen. 600 things could happen here, or did happen, I guess. Okay, so let's find some probabilities. So we're going to do some ands and some givens and some ors and stuff like that. So we have here my example A. We want a probability that a customer got a tune-up and they went to station 2. So one of the ways is to try to use a formula, but because we already have the table written out, it's way easier just to count. I mean, you could use the formula and it gives you the same answer, but check this out. Check out just by now the table is written out here and it's pretty easy to find the numbers. We want a tune-up and they went to station 2. So what is a tune-up and station 2? Well, here's all the tune-ups. Oops, here's all the tune-ups. Tune-up, tune-up, tune-up. But only one of these is station 2. This is right here, both or and tune-up and station 2. All the other numbers either don't have station 2 or don't have a tune-up, right? This number over here has a station 2, but not a tune-up, right? This number over here has a tune-up, but not station 2, right? This is the only number 40, which is both tune-up and station 2. So there's 40. How many are there total? Well, we know there's 600 total. So the answer here is 40 out of 600. And we can reduce that fraction, but I'm going to stay focused on the probabilities and not do the simplification for this last example. So 40 out of 600 with the probability that the customer got a tune-up and that they went to station 2. All right, let's change the wording a little bit. And let's say, what's the probability that the customer got a tune-up given that they went to station 2, right? So notice that I have given here instead of the and from before. So given that they went to station 2 means that 2 has already happened. We know that they've gone to station 2, right? So if they've gone to station 2, it's got to be one of these things, right? These are the only things for station 2. In fact, there are 111 services that were performed at station 2. We no longer have 600 possibilities because these guys are out. Can't be station 3 guys, can't be station 1 guys. So we don't have 600 anymore. We only have 111 because we know we are given that they went to station 2. How many of those are got a tune-up? Well, once again, 40 got a tune-up, but it's not 40 out of 600 because we were given they went to station 2. So it's 40 out of 111. 111 are the total for station 2. 40 of those match the description. They got a tune-up. All right, let's reverse this. Instead of customers that got a tune-up given they went to station 2, let's say they went to station 2 given they got a tune-up. So I reverse those things, right? And you actually get a different answer, right? So now we know we are given the fact this is something that we know has already occurred. They got a tune-up. So where are all the tune-ups? Tune-ups, tune-ups, tune-ups. Tune-ups are here. These are all the tune-ups. 60 at station 1, 40 at station 2, 85 at station 3, and 185 total tune-ups that were done. So given they got a tune-up, so we know they got a tune-up. So we know it's got to be the 185. It can't be any of these other guys. It can't be any of these over here. So we're not doing 600 because we're already told it's a tune-up. So it's got to be one of those 60, 40, or 85. In other words, it's got to be something out of 185. Well, how many of them went to station 2? Well, once again, this is the number that went to station 2, given that they got a tune-up. So it would be 40 out of 185. So this is 40 out of 185 because we know that they got a tune-up. So there's only 185 customers possible. And of those 40, were at station 2. All right, let's do a couple more. All right. Probably the customer got an oil change or they went to station 1. All right, here's where I'm going to recommend using a formula just because it gets a little bit messier when you're trying to count the overlaps. So here we go. To find the probability that they got oil change or they went to station 1, we're going to do the probability that they have an oil change. Oil changes are 228 So 228 out of, well, 600, because we're not saying given anything. So 228 out of 600. And then station one. Station one is these guys right here. So it's um, um, oops. So, or they went to station one. Station one is 100 out of 600. Sorry, I don't know what is the vertical column, but there are 100. Okay, slow down, Jim. Okay, all of these are station one. I did it right the first time. So there's 100 oil changes at station one. There's 50 tire rotations at station one. There's 60 tune-ups at station one. There's 210 events that occurred at station one. I want to say they went to station one. So there are 210 things that could have happened. 100 oil changes, 50 tire rotations, 60 tune-ups. So it's 210 out of the 600. So there's 210 out of the 600. All right. And then we want to subtract off the probability that they both occur, right? Because we could have one or the other or both, we got to subtract off the double counting. So we want to find the probability that they both occur. So for them both to occur, well, we want both oil change and so we want both oil change and we want station one. So what's the number that represents both oil change and station one? That's this 100 up here. That 100 is the number that matches oil change and station one. This number over here does not match station one, so that can't be it. This down here does not match oil change. So none of these other numbers match both oil change and station one. So we're doing the probability that event A happens plus the probability that event B happens, and then minus the probability that both happen. And the probability that both B happen, according to our chart, is 100 out of 600. And that's one of the reasons I put these answers here, to keep me on track, so I don't make little mistakes like all humans are capable of making. So that's the probability that they got an oil change or they went to station one. You can just add the two probabilities separately and then subtract off the intersection, the probability that they both happen. Okay, one last example to go. We have a given statement. So probability that a customer got an oil change given they went to station one. Again, sometimes people get D and E. They kind of read them the similar way because it's like oil change station one, oil change station one. But the key difference is in D, it's an or, and in E, it's a given, right? So we just have to be careful when we read the letters or read the words, I mean. Those little words or and given, they actually mean a big deal in these math classes, right? Because they're going to change the formula quite a bit. So just read slowly and carefully and watch out for those keywords, the or, the ands, the givens, and you'll do fine. And you'll do fine. Just read slowly and circle things like, oh, there's a given, like circle this. Okay, it's a given one, right? So what is the given one? Well, we know they went to station one, right? Because the given says there's already a fact that has occurred. We went to station one. So what are all the station one people? Oops. Station one people. These are all the station one people, right? Oil changers, tire rotations, tune-ups at station one. There's 210 station one people. So we know given that they went to station one. So we know there's only 210 people that we can consider. We cannot consider any of these other people here. They didn't go to station one, or they didn't, they didn't go to station one, period. Right? All these people are not going to be included because they don't have the given they went to station one. Now, knowing that we went to station one, how many got an oil change? Well, here's your oil change right here. 100 out of the 210 got an oil change. So my probability for example E is 100 got an oil change out of the 210 that went to station one, given that they went to station one. So that's the probability that a customer got an oil change, given that we know that they went to station one. Okay, so those are a whole bunch of examples with ands and ors and givens, with contingency tables and different events occurring. This is where we get to go at the end of the video. Go back to the beginning, double check our learning objectives. Again, the idea here of the video, hopefully you have an idea to do all these things. Explain the difference between empirical probability and theoretical probability. Calculate the probability of an event, both empirical probabilities and theoretical probabilities. Explain the difference between odds and probabilities. Calculate the probability of two events both happening. Calculate the probability of two events either or happening, and also describe and calculate conditional probability. That's the ands, the ors, and the givens. And for ands, remember we have dependent, independent, and for the ors, we have mutually exclusive and not mutually exclusive, aka mutually inclusive. Okay. Finally, we used a table that shows the relationship between two categorical variables, i.e. a contingency table, and we found the probabilities of ands and ors and givens from the contingency table. All right, hopefully this was a useful video. Hopefully it was good use of your time, and you'll reach out if you have any questions, want some more examples, any what if scenarios that I can help with. And I hope you have an enjoyable day. And perhaps I'll see you in the next video.